Okay, so this is Psych 222, and it is January 29th. And today we're going to finish off the main ideas of Chapter 2, and then next week we're into Chapter 3. Now, just a word about Chapter 2. Chapter 2 is a pretty big overview of many experimental concepts and things like that. So many of the things that we're talking about in Chapter 2, we're going to be unpacking as we go throughout the course. So recognize if a lot of these terms are kind of a little bit difficult to visualize and to conceptualize, we're going to be getting some clarification on that as we go out throughout the course. The approach taken by the book is to give a big overview in chapter 2 of principles, but you really start to understand them well as we move on throughout the course. Okay, so last time we were talking about things like surveys, experimentation, data collection, all these things that the scientist, whether social or natural, would be using to collect information. Okay, and we're talking about some of the problems with these things like non-response in surveys and all these things. So science is a really difficult thing to do. To do it properly, you need to be aware of all these things that can influence your results. Well, we talked about an example last time, and we will be talking about this throughout the course because it serves as a pretty good prototype for a lot of the things we're talking about, and that is the COVID-19 virus. So last time we said, well, maybe we have COVID-19 treatment over here. So we might treat some people with something that we think is going to cure the illness, and then one group doesn't get anything. So let's just put that down here again. So we have participants. Okay, those are participants or subjects. And some participants are going to get a treatment, and other participants are going to get the control group. Now, the control group can sometimes receive a placebo as well. So these people might receive that medication that we hope alleviates COVID-19. And these people here, they might receive like a placebo, like a fake pill. And sometimes that's done because you still want this group to receive something. It's just, it's not expected to work. And actually, when we look at the Pfizer vaccine, in their experimentation, they used a placebo for that control group. And they gave people something that was not expected to work. So that's sometimes used in experimentation. Now, the key thing here is that when you take participants, okay, there's a participant, those participants have to be assigned to conditions randomly, right? You definitely don't want to take your participants and, say put all older people here and all younger people here. That would not be good experimentation. You want to have a process of making sure that there's no biases introduced in where the participant goes. That's going to give you a comparison between that treatment and control group. Now, it's sometimes asked, why do you need the control group? Why don't you just give participants the treatment and see what happens, right? So let's say that you have participants suffering from COVID-19. Okay, so they have the illness. Well, what if you simply gave participants treatments and then observed whether they got better? What's the problem with that? So imagine we just focused on over here. Forget about the old and the young. That was just for an example. If you simply give participants the treatment and see if they get better, the problem with that is that you don't know if they would have gotten better without the treatment, right? So let's say we have, these are 50 people here that you give the treatment to. And then you observe them over the next couple weeks. So you observe them over time. Well, let's say that all 50 people get better, now completely healed of COVID-19 after a 2-week period. You may be tempted to say, wow, my treatment really works because I gave them the treatment and they got better 2 weeks later. The problem with that, as Dr. Fauci and Dr. Birx have been telling us, right, over the past 10 months, is that you don't know whether they would have gotten better without the treatment, right? And that's what the control group is for. It's entirely possible that individuals would have gotten better without the treatment. And that's why you need that control group to make that comparison. Otherwise, you simply don't know whether that treatment that you're imposing on subjects is actually effective if you don't have the control group. And that's really, really important. We cannot emphasize that enough. And one thing you want to take away from the course for sure, in terms of what good experiments are, is that idea of the control group. If you do not have a control group, you cannot start making claims about this particular group. And we'd all be surprised at how often that actually happens in research. Sometimes researchers, by mistake, will conclude that something is effective, even though they don't have a control group. And that's not very good scientific experimentation. So we want to be aware of that. What we're going to see as we move up throughout the course is, maybe 50, let me put the 50 people get better over here. So they got better. Well, maybe in the control group, 40 people got better over here. So we're going to try to be comparing these numbers over here and trying to discern whether our treatment was effective or not. Because that could be hard to tell, right? If 50 people got better here and 40 here, well, what does that mean? Did the treatment work? Did it not work? Why are these people in the range of 40 and these people 50? 50 people got better compared to 40. So the result is a little bit ambiguous. Now compare that to if 0 people got better in the control group. Well, if 0 people got better and 50 people got better here in the treatment group, so they received that COVID-19 treatment, wow, that's a pretty clear result. We can probably say there, wow, looks like that treatment must be having an effect because the result is very, very clear. But as we're going to see as we move throughout the course, statistics and statistical analyses are often used for situations like this, where the result is unclear and it's kind of ambiguous. And again, I'm going to unpack that as we move throughout the course. Here's another example. You can read that. It's about shrimp. We're going to focus on more exciting examples than shrimp and some of the stuff that the book mentions. But a good thing to do here is to look at our examples that we put on the side here, and also read this over and relate them a little bit. Again, when you're reading some of these examples, you don't have to know them in detail. Just get the feel for what they're talking about when they're describing the study. And what you want to do is you want to be nodding your head, going, yeah, that makes pretty good sense. I can see how that relates to what we're talking about. And that's a good learning check for you. Okay, we talk about fractional factorial treatment structures. Well, we're not going to talk about that. That's a very, very advanced topic. But that's when you only have a fraction of possible treatments that are actually used in the experiment. That's way beyond what we have to know. Control treatments, okay, the control treatment, well, that's when you have the idea of no treatment often in the study, which is what we're talking about. This treatment is the benchmark to which the effectiveness of each remaining treatment is compared. Now, again, control group is fine. Sometimes the book uses some pretty fancy words to describe things that you can just call the control group. It's not really a treatment in this case. It's a control group. But this also allows for possibilities where maybe they are getting a treatment, but it's regarded as not the treatment under test. So you could have treatment 1, treatment 2, and treatment 3. Maybe these 2 treatments are the ones that you're thinking is going to help against COVID-19, and this treatment is the one you're expecting not to work. And sometimes you can call that the control treatment because it's not under investigation. So there's some slight distinctions there. Okay, well, what are experimental units? Well, experimental units is the physical entity to which the treatment is randomly assigned or the subject that is randomly selected from one of the treatment populations. So again, the book uses the shrimp example in terms of objects and containers. But let's talk about human subjects, because many of us will be studying human subjects as we move on from this course. That's an experimental unit, okay? We are studying that individual. Maybe we're evaluating the person's IQ score or some other measure. That's an experimental unit. But if we take a married couple, right? They are married, they are holding hands, and this married couple can also be regarded as an experimental unit, because maybe we want to study married couples. Right? Maybe we want to study married couples. So there's one unit, the married couple, and then you have another unit, which is another married couple. That sometimes happens in research where you have several individuals and you can just kind of treat them as the same unit. Okay. Replication, well, that's how many different units do you have within the treatment and control groups? So how many married couples do you have? If the unit is simply an individual, how many individuals do you have? If it's things like shrimp containers, how many containers do you have? All of these different examples refer to the idea of replication. Okay? And we're going to see as we go on throughout the course, replication is a good thing because it provides you more information. You definitely don't want to be comparing one married couple to another married couple. That's not very much information. You want to have a lot of married couples. You want to have a lot of people. Replication is good. Measurement units is a little bit distinct from the experimental unit, but oftentimes they're the same. This is the physical entity upon which a measurement is taken. So let's go back to the married couple here. You may be measuring something on this person and on this person. Well, those are the measurement units, okay? Because you need the score for this person and the score for this person. You're measuring on each of those units, even though this is still possibly regarded as the experimental units. Okay. So some distinctions to keep in mind. You can read over that example. Experimental error, that's a pretty important concept. And again, that's a concept that'll make more sense as we continue through the course and unpack how to do statistical testing. But let's look at an example of what experimental error is about. So I'm going to go back to my participants randomly assigned to treatment or control. And again, these people, maybe they suffer from COVID-19, and we're going to treat some of them, we're not going to treat some of them, and we want to see if our treatment is effective. Well, what are we treating? Maybe we're trying to treat temperature. We want to treat COVID-19, and we're looking for a temperature change, right? Because we know that fever is associated with COVID-19. So maybe if our treatment is working, we expect temperature to decrease, let's say, for example. So let's say that on this individual has a temperature of 98, this individual 99, and this individual 98.3. Okay, there's 3 individuals here at different temperatures. These individuals, just for the sake of example, I'm just going to make these temperatures pretty high. These are, too high for good health. But let's say that the COVID-19 is actually having that effect, is producing very high temperatures. Well, the idea of experimental error has to do with what's happening within these particular groups. Now, we can probably say from this example that it looks like our treatment might be effective because it's reducing temperature, right? It looks like it's reducing temperature because people in the control group have high temperatures. People in the treatment group have relatively lower temperatures, almost about normal, right? I believe normal is about 98.6 or so. The idea of experimental error, though, is this idea here. Why is 98 different from 99? Why are we seeing a difference within the same group, that they're different from one another? We have ideas as to why we're seeing differences between groups, but why are we seeing those differences within the group? And that could be due to many, many different things as to why this temperature is different from this one. The reasons, well, the book mentions a little bit. Here's an important one: the natural differences in the experimental units prior to their receiving the treatment. Maybe this person just has naturally a little bit lower of a temperature than this person. Now, maybe some people run a little bit cooler than others, whereas other people it's a little bit higher. And if we say that the average temperature is about 98.6, or the normal temperature, well, we know that temperatures are going to vary around here. Okay, that shouldn't be a percentage. 98.6 Fahrenheit. We know that temperatures are going to vary around there. Not everyone's going to have a temperature of 98.6. So in other words, there could just be differences between people that is producing the differences within these groups. Same thing over here. Why is 103 different from 104? Could be many reasons, but one could simply be some people just are a little bit hotter than other people. But there could also be other things at play. There could be an infinite number of things at play. And another one is the variation in the devices that record the measurements. Right? There could be differences in thermometers used. And when we talk about things like that, when we take our temperature with a thermometer, we think that the thermometer is kind of like fault-free, but that's not true. The thermometer may have a little bit of error, producing a little bit of differences each time it takes a temperature, even though the true temperature is the same. So let's imagine this. I'm going to take temperature on time 1, and I'm going to take temperature on time 2. There's a 5-second elapsed time from time 1 to time 2. So you get up in the morning, you take your temperature, and then you take it again 5 seconds later. Well, your temperature might be different from time 1 to time 2. And it may not be due to the fact that your true temperature has changed. Maybe your true temperature has remained the same. Maybe it's simply the measuring instrument that's recording a little bit of error in there. So the difference in temperature from time 1 to time 2 could simply be due to the measuring tool. And that's that advice. Okay. Some other things here. The variation in setting the treatment conditions. Well, depending on how you set those treatment conditions can contribute a little bit. I mean, how much of the drug are you giving to this treatment condition? If we put another treatment here, treatment 2, how much drug are you giving here? So there's going to be some variation on how you set treatment conditions, and that can contribute to difference in scores as well. And number 4, the effect on the response variable of all extraneous factors other than the treatment factors. Just because you gave these people a treatment and these people a control, there could be a whole bunch of things that are still producing differences between scores, right? So not only measuring tools, but maybe what else? This person maybe didn't get very much sleep last night, and that maybe produces a slightly different temperature than this person. Now, maybe this person eats a lot of spicy foods. This person does not, assuming that could influence the temperature. Who knows, right? There's a whole bunch of things that could be at play as to why those scores are different. And all of that, we're kind of putting under this rubric of experimental error, but it's important to realize that error here, error does not mean mistake, right? It doesn't mean mistake. So you definitely don't want to think errors are necessarily mistakes. Errors are those differences we're seeing that are attributable to a whole bunch of things. Okay, and we're going to unpack that as we move throughout the course. So another example there, you can read through and see how they compare to what we just talked about. Well, we said that experimental designs are really, really important, right? Well, we're going to define what's called the completely randomized design. So a completely randomized design is used when we're interested in comparing T treatments. Well, in this example we're going to compare tire brands. A less exciting example or interesting example, yet we want to talk about the tire brands. What we just did for our experiment for the COVID treatment, well, that's a completely randomized design as well. Okay, and we're randomly assigning people to conditions, and we're comparing the different treatments. Even if one of the treatments is a control condition, we're still said to be comparing the treatments. Well, let's look at the tire brands here. We want to compare tire brands. Well, let's look at this example. Imagine you want to see which tire brand is best. You have tire brand A, B, C, and D. Well, how much do they wear? We all want to buy good tires. You don't want to buy tires that wear out after 10,000 miles and cost you $500. You want to buy tires that last like 80,000 miles and have really good tread quality, especially like if you're driving on slippery roads. You want to make sure that your tires don't wear out too fast and they're very, very good. Well, what do we think of this particular setup? This is a mess, right? Now, why is this a mess? How are you going to know which brand is working? Right? There's some confounds in here. For one, you have different cars, and then you have different brands within each group. So this becomes really, really difficult to know which tire brand is going to work the best. And one of the main reasons here is maybe the different cars are wearing tires at a different rate. Okay, so let's give an example here. We know that car number 1 maybe has good alignment, right? When you align your tires to help regulate your tire wear and make sure it's all even, maybe car 1 has really good alignment, but car 2 is poor alignment, right? That's got poor alignment. That says poor alignment over here. So we don't want those factors influencing the tire wear. We want to kind of get rid of that. So how about we do this? How about we produce blocks? And these are called randomized blocks, where you have car number 1, car number 2, but then you have the brands over here. So this is considered to be a block. And then you have another block over here, okay? And that's what they're talking about here. Each treatment appears in every block, okay? So when you're doing this, that could be considered a block. If you were to compare cars, you can also say, well, there's car 1, and I'm going to compare brand 1 to brand B to brand C to brand D. So there's a couple ways you could run this experiment. But the idea is that by producing these blocks, you're helping kind of regulate some of those confounds, okay? And this is an example where you can actually study 2 things depending on which one you're interested in, because you could compare those cars on how they're wearing out tires, or you can start comparing the different brands by producing these given blocks of cars. Okay, so that's a general concept of what they can do in experimentation so that you don't have this messy situation over here where it's really hard to tell because of you have different cars, you have different brands. You want a nice, neat setup over here, okay? And we'll talk a little bit more about block designs later in the course, but that becomes a little bit of an advanced subject as well, so we'll only touch on it. Latin square design, not imperative. You don't have to look that over. That's just a little bit more of a generalization of that blocking idea. Okay, so factorial treatment structure in a completely randomized design. We're talking about factors here, okay? We're talking about factors. Now I'm gonna put y is equal to x, and I'm gonna say that y is equal to COVID-19 symptoms. So there's our response, right? We're trying to measure COVID-19 symptoms, and I'm going to say that COVID-19 symptoms is a function of treatment, yes or no. So again, our classic example of the COVID-19. That's a factor, right? That's the treatment factor. Did you get the treatment? Did you not get the treatment? Now, in some studies, we may want to include a second factor. So there's one factor. We may want to include a second factor in there. Well, what's another factor we can put in aside from maybe treatment, right? What else could we randomly assign people? Maybe we give them some rest, right? You assign them to different amounts of rest. You know, you say, well, we want you guys, people sleeping 10 hours a day and you people sleeping 5 hours a day. Let's see if that has an effect on COVID-19 symptomology. So that could be another factor. What's another factor? Well, we could go on, right? We can say, well, did you receive the vaccine? Did you not receive the vaccine? There's a whole bunch of factors that we can include when looking at a particular study. Okay, and that's what we mean by that. Again, the book has some good examples of factors. One approach here that the book talks about is a one-at-a-time approach. This is examining the effects of two or more factors on a response is called the one-at-a-time approach. So to examine the effect of a single variable, the experimenter varies the levels of this variable while holding the levels of the other independent variables fixed. So you can look at one particular factor at a time while trying to hold the other one constant. So maybe you look at this particular situation here where you're looking at whether there's a treatment effect, but you're trying to hold rest fixed at a particular level. And that could be regarded as the one at a time approach. Okay, more examples. Talk about yield and bushels and things like that. Here's the results of a factorial study and the concept of an interaction. So they're measuring corn yield here. That's the response. That's the response. And they have phosphorus level here, and this is nitrogen, different nitrogen levels. So how much yield are you going to get for different amounts of nitrogen and for different amounts of phosphorus? That's what that's saying. Now, again, nitrogen, phosphorus, well, let's do this instead. Treatment 1, treatment 2, and treatment 3 for COVID. Did you receive treatment 1 or 2 or 3 for COVID-19? Let's modify the example a little bit. What are these three groups? Well, nitrogen 40, 50, 60. Maybe we have the rest that we're talking about, right? We have the rest. So rest, how much rest? 6 hours, 8 hours, or 10 hours per day. Right? You want people to have different amounts of rest to see if they get better. So maybe that's 6, 8, 10. So we can see that this is an interaction because we can monitor the response. In our case, maybe symptomology, symptoms, say fever, right? That's the degrees Fahrenheit. We can monitor how fever changes across COVID-19 treatments, but we can also monitor it simultaneously how it varies across rest. So what we're looking at here for this first mean, again, these would be high temperatures, so maybe we want to stick to corn yield for looking at this axis, but the principle is the same. So there we go, treatment 1 for 6 hours of rest. That would be the mean, right? And then we see as we go from treatment 1 to treatment 2, look what happens. It goes up. And then to treatment 3, it goes up to this value here. Those are all for the people who are getting the 6 hours of rest. And then we can look at for the 8 hours of rest, what happens to the means. It goes from here to here to here. And then for the 10 hours, goes from here, here, and here. So what this plot is showing you is how two factors, whether it's phosphorus level and nitrogen or treatment for COVID-19 and amount of rest, so maybe the whatever treatments we're giving for it, we can observe how those are behaving in the same plot. And this concept of an interaction, is the idea that at a given treatment level, well, we see one difference here, but look what happens as we go to treatment number 2. We see this one decreases, this one decreases, this one increases. These differences here are not the same as the differences here and are not the same as the differences here. That is generally known as an interaction. And we say that the treatment for COVID-19 is interacting with the degree of rest, right? And again, that's the idea that the differences at one level of the factor are not the same as differences over here. Now, when you see a plot like this that looks like it's got a whole bunch of non-parallel lines in it, that definitely suggests the idea of an interaction. Let's clean this up a little bit so we can see what a no interaction looks like. No interaction would be something like, something like this, right? There's no interaction. That's a poorly drawn line. Let me see if I can just connect those dots. That's a little bit better, not perfect. See, this is the idea of no interaction because you're at treatment 1, treatment 2, treatment 3. There's an increase for that group receiving 8 hours, 10, and 12. There's an increase here, there's an increase here, there's an increase here, but nowhere are we seeing differences from treatment to treatment. These differences are the same. We're not seeing the mean differences switch all of a sudden as we go from treatment 1 to treatment 2. See how we've got some consistent differences here? That's the idea of no interaction. So it's said that when you have parallel lines in a plot like that, you do not have an interaction. But when it's messy like this, like up here, wow, you have an interaction in your plot, okay? Again, the book is just talking about this in a general sense. We will talk a little bit more about it towards the end of the course. So in April, we'll be talking about this a little bit. For now, you're just looking at it, you're reading it over, and you're getting that general concept. There's the example of no interaction, right? There's another example. We did the straight lines just above. That's an example of no interaction. Why is there no interaction? Because look, those differences, the same over here. Even though the means went up a little bit, we see those differences are constant over here. Okay, there's no interaction. Okay, so we talk about these factorial ideas. Well, the factorial idea is the idea when you have those different treatment structures. So you have treatment yes versus no, and then what was the other one? Rest. Let's just put yes, no, for instance. We could put the 8, 10, or 12 hours if we want, or we can just have rest, yes, no. Maybe you're not allowing people to have any rest, and some people you are. But we have to be careful. That would not be very ethical because people do need to rest. This is a factorial idea because you have more than one factor, right? You have 2 factors, so that's why we're talking about as a factorial treatment structure. You can have very complicated designs. You can have 3 by 3 factorial treatment structures, okay? There's pretty much no limit to how many factors you can talk about. We're just going to stick to talking about 2. And again, we'll talk about it more in the course later. We talked about the block design a little bit, and that was referring to producing those groups of subjects or participants or cars or tires, as we were talking about. Controlling for experimental error, and this is a little bit beyond what we need to know, but sometimes in models, they try to control for that experimental error by introducing covariance. So remember we said what experimental error is all about. Well, if we just go into our temperature group again, 98, 99, and 100. Remember, these people had different temperatures, but we didn't know why, because they were all in the treatment group. Remember that concept we just talked about above? Well, maybe one reason why they actually have different temperatures is because they have different baseline temperatures, right? Some people run a little bit hotter or cooler than other people. Well, maybe we can take that into account. When we try to remove that variability, we're controlling for a covariate, because that baseline amount of temperature would be called a covariate here. Another issue is maybe older people have higher temperatures than younger people. I don't know, I haven't looked at that, but maybe that's true. If that's true, and this person here is 7 years old, and this person happens to be 50, and this person is say 25, then maybe we want to kind of try to control or covary out the idea of age from the particular model. And those are generally known as covariates, because the covariates can introduce a lot of error into our study. And sometimes we want to remove that error. So that's an idea of the covariates. Okay, experimental procedures. I think that's pretty much where we're going to stop for this, this chapter. If you are interested in learning a little bit more about experimentation, you can read the rest of the chapter, but I think we've covered enough concepts for this chapter. And as mentioned, the book is very, very, very big. That book can last you a long time as you go into future studies. So we definitely are not going to be covering everything, and focus on what's in assignments and then relate it back to the book, because what's on assignments is what's going to be kind of targeted on the evaluations and tests. So look at the assignments and then go back to the book for clarification, go back to the lectures for clarification. Okay. I just want to leave with one point for today. When we talk about experiments and procedures and things, I just want to highlight the importance of that. So when we started off today's class and we had those participants and we were putting the participants in the control, or this was the treatment and control conditions. Again, the main principle to take away from today is that idea of experimentation is really, really important. And want to emphasize that, and I will be emphasizing it throughout the book. Let's put it this way. That vaccine, right, that vaccine developed by Pfizer, we would not know if that vaccine worked or not if they did not do an experiment. So it's really, really important that if you want to know if something is having an effect, if the vaccine is working, if the COVID-19 treatment is working, you've got to hear the word experiment. Otherwise, you usually don't know for sure if it's working. So, you know, in the age of COVID that we're in, if you hear about a news report and they say, you know, we have a new treatment for COVID-19, you are definitely wanting to hear the word experiment or experimental design to know if they've actually have any evidence. If they do not say experiment and they do not do an experimental design, then you have to be very, very cautious about whether you believe the claim that's being made. Okay, so experiments, really important. So I'll leave with that point for today. Next week, we are into Chapter 3, and we will see you then.